Today I'd like to talk about binomial distributions. So please turn in your study guide to the binomial distributions section. Now we begin by talking about the concepts behind a binomial distribution. In a binomial distribution, each trial results in one of two mutually exclusive outcomes. We either get a success or we get a failure. And not only do we define our outcomes as a success or a failure, we have a fixed number of trials that are performed in a binomial experiment. The outcomes of these different trials are independent from one another. Thus, the probability that a trial results in success is going to be the same for all trials. So the last two statements kind of go hand in hand. Outcomes of different trials are independent. In other words, a previous trial's result will have no impact on the outcome of the next trial. And the probability that the trials will result in success or failure is the same for all trials. The binomial random variable x is defined as the number of successes out of the fixed number of trials. All of these ideas are essential to defining a binomial probability. Once again, each trial results in one of two mutually exclusive outcomes. We either have a success or we have a failure. We have a fixed number of trials. The outcomes of our trials are independent from one another. And the probability that a trial results in success or failure is the same for all trials. Now, let's talk about some examples here and decide whether these examples here are binomial distributions. Suppose we toss a coin 10 times and count the number of heads. Now, let's go back through the components that make up a binomial distribution. In a binomial distribution, each trial results in one of two mutually exclusive outcomes. And certainly that's the case here. When we flip a coin, we're either going to get a head or we're going to get a tail. Now, do we have a fixed number of trials? And the answer is yes. We're flipping a coin 10 times. So we have 10 particular trials in this experiment. Next, are the outcomes of different trials independent from one another? And yes, they are. Regardless of how many times I flip a head, the result of my next coin is going to be independent from the previous one. That is, if I flipped 9 heads in a row, the chance of me getting a head on my 10th flip is still going to be 1/2. And because my trials are independent from one another, the probability that a trial results in success is going to be the same for all trials. So all of the criteria are met here, so we certainly have a binomial distribution. Now, what about the next example? Suppose we deal 10 cards from a shuffled deck and count the number of red cards. Let's go ahead and go through the components that define a binomial distribution. Each trial results in one of two mutually exclusive outcomes. And that's certainly the case here. We're either going to get a red card or a black card. Do we have a fixed number of trials? Yes. We're dealing 10 cards. So we have 10 trials. Are the outcomes of different trials independent? And here's where we run into trouble here. If we're dealing 10 cards and we're not replacing those cards back into the deck, then our probabilities are constantly changing on whether a card will be red or black. So the outcomes of different trials are not independent. They're actually dependent on what previously happened. Thus, the probability that a trial results in success is not the same for all trials. So here, we do not qualify for a binomial distribution because of our probabilities. The probability does not remain constant here. Now, what about the next example? Suppose two parents with genes for O and A blood types are present, and we count the number of children with blood type O. Now, once again, each trial does result in one of two mutually exclusive outcomes. Either we have type O blood or we don't have type O blood. However, the second criteria is not met. We do not have a fixed number of trials. We're simply counting the number of children with blood type O. So here, there is not a fixed number of trials. Let's talk about the number of heads on 3 tosses of a coin. We're going to let the random variable x be the number of heads that are tossed on 3 tosses of a coin. Now, let's create our probability distribution. Now,